This is exercise 128 in chapter 8 of our textbook, where it says that according to the National Center for Health Statistics, the average height of females in the United States is 63.7 inches, with a standard deviation of 2.75 inches. Using the heights for the random sample of 50 female American health professionals in a previous exercise, test the claim that the mean height of females in the health profession is different from 63.7 inches, the mean height of all females in the United States. Use a 0.05 level of significance. So we are testing a claim, which basically is telling us to run a hypothesis test. The other word we look for that's a signal to run a hypothesis test is when they ask if there is evidence. So in step 1 of our hypothesis test procedure, we must state all the pertinent parameters and statistics and identify the null and alternative hypothesis. So I clearly see that they claim that the average height of females in the United States is 63.7 inches. So they're making a claim about a population mean, which means we're talking about mu, and they're saying that mu is equal to 63.7 inches. The statement of equality always belongs in the null hypothesis. Because of the fact that they identified that we want to test that claim to see if we have evidence to say that it is different from 63.7 inches, then they are identifying that they want us to run a two-tailed or two-sided hypothesis test. We don't know if it's going to be more, we don't know if it's less, just that it's different, which means in the alternative, we're going to say that the mu is not equal to 63.7. Now, anytime we use a variable in our hypothesis statements, it's important that we define that variable. Mu is an average. We just want to be specific about what it's an average of in this case. And mu has been defined as the average height of females in the health profession. Now, other things that we should also identify in the state is what is our sample average, our X bar. That was calculated in exercise 1. It was 64.78 inches. We're also given the number in the sample, n is 50. We're also given the value of the standard deviation in the population, sigma, is 2.75 inches. We're told to use a level of significance equal to 0.05. That is our alpha level. So that completes our step 1 of this hypothesis test. In step 2, we know that we need to complete the plan. And the plan is to verify the conditions that are important to be met in order to perform this hypothesis test confidently. So 1, we need to be told that the sample was obtained randomly. And it was stated that a random sample was obtained from the population of all women in the health professions. Can we assume that our sampling distribution is approximately normal? We can, because n is large, or greater than or equal to 30. And then, is it safe to assume that these women have been chosen independently of one another? And this is where we want to check to make sure that our sample size does not make up more than 10% of the population. So our sample size is 50. If I multiply 50 by 10, then that means that my sample size of 50 would be 10% of a population that contains 500 women. Well, I believe it's safe to assume that there are more than 500 women in the health professions. So our plan is complete in that random, normal, and independent have all been satisfied. When we go to do the do, we need to calculate our test statistic using our test statistic formula, and then use that test statistic and look it up in our table to determine our p-value. So if I plug in all the values I wrote down from my step 1, my x bar was 64.78 inches. My claimed mean in the null hypothesis was 63.7 inches. My standard deviation of the population given in the stem of the problem was 2.75 inches. And my sample size was 50. So we're typically in the habit of calculating the standard error of our statistic first. When I divide 2.75 by the square root of 50, I get a standard error equal to about 0.3889. My numerator, the difference between my sample average and the claimed population average, would be equal to 1.08. So my test statistic can be found by taking 1.08 and dividing by the standard error of my sample averages, 0.3889. And I get a test statistic of 2.78 if I round to 2 digits after the decimal point. So the question is, what does that mean in this hypothesis test where we have a two-tailed alternative? Let's picture it. I've got a normal distribution. The claim is that the average height is 63.7 inches. And the average height of the sample of women that was selected here is almost 3 standard deviations above the mean. Now, because this is a two-tailed hypothesis test, in that I chose to use a not equal to in the alternative because I was just looking to see if I have evidence of a difference, then that would basically mean that I could end up in this tail up above my test statistic of 2.78, or I might have been as equally as far in standard deviations below my test statistic of negative 2.78. So I basically want to determine the area in each of those tails. Well, each of those tails contains the same area, so if I can find the area in one of them, I merely need to double that area to get my p-value. So when I look up a z of 2.78 in my table, I see the area below is equal to 0.9973. I want the area above, so I need to take 1 minus that answer to determine that the area in that right tail is equal to 0.0027. That means the area in this lower tail that is also 2.78 standard deviations from the center is also 0.0027. So to determine my p-value, I just need to double that area, and I get my p-value is equal to 0.0054. So that appears to be quite a small p-value. It's very unusual that we would have a sample average this different from what is claimed or more different from what is claimed if what is claimed is really true. And therefore, because our p-value is less than the level of significance given in the problem, which is 0.05, we're going to reject the null hypothesis. So when we state our conclusion, which is our fourth and final step of a hypothesis test, our first thing to include in that statement is what our decision is about the null hypothesis. So we will reject the null. That's first. Second, it's important to justify why we've made that decision. Well, when P is low, we reject the hoe. So we'll say something like we reject the hoe because P is low or less than the alpha level given in this problem, which is 0.05. So second is our justification. The third thing in our conclusion is to state in context what we believe to be true of the alternative hypothesis. Well, if we're rejecting the null, then we believe the alternative is true. So we can say that we have sufficient evidence to state that the average height of all females in health professions is different from 63.7 inches. So we rejected the null, so we believe we can say that the alternative is true. Remember, we haven't proven this, but we have very strong evidence that that is in fact the case. So that is the third part of our conclusion. What did we decide about the alternative hypothesis?